Hi there. I'm going to try in this video to explain a bit about what stoichiometry is, as well as maybe do an example of one of the questions. Now, stoichiometry, speaking as a chemistry teacher, is a great topic to teach because it brings together all of the stuff that we teach in our beginning chemistry parts about writing equations down, how to balance them. You've got to balance your charges to make your compounds. It really brings everything all together in one spot, and so it's really a fun part to do, and there's some great labs we can do. But on to the idea of stoichiometry, and other than the fact that it's really fun to just say, you're looking at it there, and stoichiometry, fancy words, what you're trying to do is use balanced reaction equations to determine the quantity or how much of one chemical or reagent in a reaction from other stuff, other data that you know. So if you knew how much of one compound is being used, you could predict how much of another compound is being used using this method of stoichiometry. It's got a lot of useful purposes in chemistry, and I'll try and get to the point. So we'll just get rid of our screen shade. So why are we using a balanced reaction equation? Well, in a simple way, if we looked, if you were to take one bicycle apart, one bike, you could break that up, a decomposition reaction, a pretty simple way, into two tires and one handlebar. And it's balanced, you see, one bike, two tires, one handlebar. That's a decomposition reaction. You know for every one bike you get two tires. So if you had 10 bikes, you know you're getting 20 tires and you know you're getting 10 handlebars. If you had 100 bikes, you'd have 210 and 100, handlebars. That relationship is always going to be true. No matter what number you have here for bikes, you're always going to have the same number of handlebars. So there's a ratio there of 1 to 1 for bikes and handlebars. And the ratio for bikes and tires is 1 to 2, meaning there's always twice as many tires. Regardless of what exotic number you get here, even it doesn't matter what it is, any number at all, it's going to be twice as big for tires. The same analogy could be made from a cheese sandwich. There's more toppings on here, but for any one sandwich you have, you get two slices of bread, one slice of cheese. That would be what makes it up. And so if you knew that you had 400 sandwiches, you know how many slices of bread you're getting. Twice as many, 2 times the one here. So you get 800 slices of bread from 400 sandwiches. So if we looked at a chemical reaction, enough of this stuff here, let's get down to the chemistry. If you had aluminum oxide, so aluminum oxide, and it's a decomposition reaction, so it breaks up into aluminum and oxygen gas. Well, you have to write aluminum oxide as a chemical. So if you need a little review of that, I can try and quickly do it. You'd write the symbol for aluminum with its charge, oxide with its charge. We call it a switch rule, where you could put your 2 here to make and a 3 there. Thus, you'd have a total charge of -6, a total charge of +6. Your compound would be balanced. Aluminum oxide is Al2O3. We'll bring that back. Aluminum by itself is just Al, and oxygen is a diatomic element, meaning when you get oxygen as a gas, it actually bonds with itself and is O2. Now you have to balance this guy. I would tackle it with 3 oxygens here and 2 there. I would like to make 6 of each. If I put a 2 as a coefficient in front of aluminum oxide, then I would get 6 oxygens. I could put a 3 here to make 6 oxygens. That, however, though, messes up our numbers of aluminum. We have 4 aluminum atoms on one side. We need to have 4 on the other. So there's my balanced reaction equation, where I've got, I'll just erase it and drop back in. For every 2 aluminum oxides that I use, I get 4 aluminums, and I also get 3 oxygens. So there's our mole ratio, our ratio of numbers, that for every 2 of these, I get twice as many of those. So I get 4 of them. Now the 2 to 3 is a little bit harder, right? You get half again as much. If you had 20 here, you'd get 30 there. for particles or even moles. And we won't talk about the mole concept. I'll assume we have that concept down. So now if we had the question to actually get to the interesting part of this, we're halfway there for my time. If 25 grams of aluminum oxide, so if you know underneath aluminum oxide you write your 25 grams, and you're going to completely decompose, how much aluminum will you get? Well, this is what was given, and in stoichiometry you're always going to be able to use what's given to figure out what you want or your unknown. This is what we're looking for. So what we will do is rely on the molar mass of aluminum, which is 2 26.99s and 3 16s off your periodic table. So your molar mass is 101.96. See other videos I've done if you want help doing molar mass. Our formula here, N is mass over molar mass. I use a symbol like that for my capital M's. So you'd have 25 grams, decimal in there, divide by 101.96. I don't have that one worked out ahead of time, so we'll bring it up here, turn this on. We have 25 over 101.96 gives us 0.245. So N equals 0.245 moles. Now, what am I looking for, though? I want to use this number. If I have 0.245 moles of aluminum oxide, my balanced reaction of 2, 4, and 3 here tells me that for every 2 of these, I get 4 of them. So I like to use a mole ratio from a balanced equation and see that I get 4 over 2, or twice as much. Twice as much aluminum as aluminum oxide. So my moles for aluminum, for this guy here, my moles for that is twice as much as the other number. Moles comes in here, and you double it, 0.490. Now that's just the moles of aluminum. If you want to get the mass of aluminum, we rearrange our other equation. It's moles times molar mass. So you take your 0.490 and you multiply by the molar mass of aluminum, which is 26.98. We put a rate in there, 26.98 grams per mole, and we'll get an answer in grams. So we'll bring up our calculator, shove it to the side. So we needed to double that number. So 0.490 times 26.98 gives me 13.23 grams. So it turns out that if you have 25 grams of aluminum oxide, you get 13 grams of aluminum. Now, it's not true that you could say, yes, there's twice as many molecules. There's 4 molecules of aluminum, but it doesn't mean there's twice as much mass. It's only true for how many particles there are, not for how heavy they are. This particle is obviously much, much heavier than the aluminum, right? Clearly, this would have a higher mass, but the same number of particles is what your mole ratio tells you. For every 2 particles here, we get 4 there, but it's not true for mass. That's why we do a mole ratio. So hopefully this helps any of you out that have been working on these, and there's lots of types of stoichiometry questions. This is just one type where we call it mass to mass or gravimetric stoichiometry. I hope you've got something out of this.